Okay. I just realized, you don't have your foundations, so you cannot finish your project. So here is a short version, well, not that short, but a simplified, at least, version on foundations that we're going to look at. The last part here still hasn't been developed, so we don't have that, a lot of that, but we have most of it. So let's just start with it. Footings, of course, are those elements that you don't see in your buildings. Once they are built, they're covered, and so you don't see them. But this is the key of it, right? You don't do a good foundation, your building will sunk or will tilt, and you will have lots of problems, right? And the main problem, of course, is settlement. Right? You start settling, things break, and produces bad service, and so that's really one of the issues. In Port Aransas, they did one building, for an apartment building, and that was a big lawsuit. The building started sinking, and they had to demolish the whole building just because of settlement. All right, so very important. Okay? So we're going to look shallow foundations because there is also deep foundations, which are your drill shafts and piles and all that. But we're not going to do that. This one is going to be shallow foundations, and actually it's going to be even simplified than what I said here. Okay. And this is really a design. In your foundations class, it's more of a geotechnical class. So what you learn there is the soil's properties, not so much the design of the foundation. All right. So the one we're going to concentrate on is the isolated spread footing. Okay? And so this one either looks like a square or a rectangular picture, right? And very typical of lots of foundations that don't need, something very deep, right? And so that's the one where this is the one we're going to concentrate on. So for your project, you should be doing one like this, a square footing, and hopefully, right, you have picked a square column. Right? I don't see any reason for you to pick a rectangular column. All right. So let's do a square column, a square footing. That's the simplest. Then you have the strip or wall footing, which also is pretty simple. Okay? So we might do an example of this. There is the combined footings, when you combine because the areas overlap, right? And so now you make it one big footing. And you have different kinds. Sometimes what happens is you are at the property line, especially in downtown areas, things that are very crowded. And so your column has to be at the edge of the property line, but that creates eccentricity. And so you join it with another column to kind of balance that. Okay? There are different types of combined footings. You can make rectangles, you can make trapezoidals. It depends. Okay, that's more about money, right? Because this one you have to form it and all that, so it costs more money. Mm-hmm. The strap footing is similar to the combined footing. The difference is that you join the two footings with a beam. So this is actually a beam. Okay, and so this means that it's going to bend, it's not going to touch the soil. But is joining the two are going to avoid the eccentricity due to a column near a property line. The mat and raft foundation is a bigger one. This is covered lots of columns, and usually, is when your footings are taking about 50% of the floor plan, then definitely you want to do that, right? Some people go even at 33%, and you start putting these mat footings. Okay? And buildings, there are buildings that use this. Some buildings use it. Actually, our lab, right? Our lab, there for the structural lab, the new lab, that's a big mat foundation, all right? We use it for storage tanks, heavy machinery, chimneys, okay? And typically it's a solid slab, but it can have a combination of beam and slabs, okay? The one in our lab is a combination, okay? It has both. Because it has a floor, some beams, some walls like beams, and then the actual footing, right? So if we look at the ECI now using more modern tools than mine, shows you some pictures of this here your strip footing. typically walls, right? Your isolated footing, your combined footings. Sometimes because the soil maybe is in a slope, you may have to slope your footing. Okay, that happens. There is the mat foundation, right, in there. And these are the piles, and we're not going to do that. But the cap is part of the design too. Okay? And then in this chapter, ACI talks also about retaining walls. All right, so how are we going to look at the soil pressure distribution? I mean, that's what we're looking at, right? And the soil, I mean, is not uniform, so it creates different issues. So that's one of the problems. So here is your mat footing, different kinds of footings with beams, right? So the distribution you can see is not uniform, all right? It varies. You have a clay, you tend to have higher pressure at the ends, less pressure in the middle. You have a sand soil, there is more pressure in the middle, less at the ends. Okay, we could design for this, right? But you're already telling me that, right? You're already thinking about it. No, that's too complex, right? Yes, you can do it. You can do your integration. You can do all this calculus 3, calculus 4, calculus 5, calculus 6 if you want, right? Find your forces and all of that. No, we don't do that, right? We are going to make this an equivalent average rectangular pressure, right? And that's how we're going to design. How do you find the value of that average rectangular pressure? That's what you're going to learn in your foundations class after your geotech, right? So that's what you're going to get. Usually you get it from a geotechnical report. So the people that specialize on that, they will give you those numbers. Now, the bearing capacity of soils, still giving us an allowable pressure. So now we're going back to the concept of the factor of safety. Okay. However, this is changing fast. So probably the next cycle of codes, it will be ultimate loads. All right. But for now, allowable pressure. So what this is your ultimate value, you're going to divide by a safety factor. Safety factors vary depending on the type of soils. I mean, soils are very sneaky. So yeah, you want to be very careful. So some values from 2.5 to 3. The geotechnical engineering will give you the report, right? The geotechnical report with the site and how are the recommending pressures. Now you are doing a preliminary study. You don't have any values here. Depending on the type of soils, you can pick up some values for your pressures. Okay, so this is just guess. Okay, don't think, oh, I got it and it has to be this. No. Okay, this is kind of an average of the whole thing. Okay? So yeah, so this is just to start. Okay? You should have at least one test done in your site to determine your pressure on your soils. At least, okay, one test. Okay. And that will depend on the size, of course, of your structure, right? But you need to test your soils to determine your actual pressures that you can put on that soil. All right? Okay. So the technical reports and even the codes, right, are specified as gross areas or net areas. So we need to differentiate between the gross and the net. Okay? A gross pressure will include all the loads that are going to be transferred to the footing, right? Which means the weight of the soil that may be on top of your footing, the weight of the actual footing, and the applied structural loads. And if there is any surcharge on top of that, that needs to be included. A net pressure is due only to the applied structural loads. So it's only to these guys right here, okay? So these are eliminated from the value. Why? Because the weight of the soil is a uniform pressure, right? And so just think about it. I mean, if I have a uniform rectangular pressure going up and I have a pressure going down that is also uniform, they are subtracting each other, right? So I can do that subtraction right from the beginning, and what is left is what will carry the load in my column. So that's the concept. So the allowable pressure gross accounts for the weight of the footing, any weight that is on top of the footing, okay, and the loads coming on your columns. The net pressure will be only the loads on your columns or your structural loads, right, applied to your footing. The rest has been subtracted out because they are the same kind, right? So they're uniform loads, they can be subtracted. And so that's how we do it. So, so then your unfactored gross loads, total loads, divided by the area of the footing has to be always less or equal than your gross allowable value, right? And so what that means is you have to have your service loads, right, coming from the column, divided by the area of the footing. Now this is a problem, right? Because we are designing our building with factor loads. Our reactions, right, are factor loads. But for the footing, I need service loads. So right there, we had to change our reactions into service values. We had the weight of the footing, the weight of the soil, and any other surcharges that may be applied to this structure, right? A surcharge, for example, will be something like, if I go here again, let's say you had a footing here, you have more soil here, and here on the top, you may have maybe a parking area, big area. So you park here, maybe big trucks. So that pressure from the big trucks has to come here, right? Okay, so that's a surcharge. Okay? So that's a special area, a special load applied to there. Okay. The other way to do it is that you only look at your loads from your structural coming from your columns, right? But that means to this gross value, you need to subtract the weight of the footing, the weight of the soil, and any surcharges. Okay? Which this now, all this, becomes your net pressure. Okay? So this is important because sometimes in the geotechnical report, they will give you a net value. Well, I mean, what they use to find the net value, what were the values that they put here, right? So you may want sometimes to call and ask and make sure you understand what value you are getting. Okay? All right. So your QU net then simply your factor structural loads. This is now QU net. Okay. So divided by the area of the footing. This is the value that we're going to use now to design the footing. Oh, wait a minute. So what is this allowable and U now? The allowable, right? The allowable is used to find the area of the footing because that's what you need. You need to have some area, right? So your pressure will be okay. So the allowable values are only used to find this area. Once you got this area, you had to design now the footing. But the footing is a concrete footing. And concrete is designed using factor loads, right? So now we had to factor the loads back again, right? With the area that we found. And now we calculate an ultimate pressure, a factor, that's the U value here, right? A factor net pressure. Net because we're only using the factor structural loads. So only use that one, right? But factor. So now it becomes a net pressure. Okay? So we get our loads from the building, reactions. Now, unless you run a case unfactored, you will have factor reactions. Those need to be changed to service in order to find the area of the footing because you know this number, right? That will be given in your technical report, right? You know now your reactions and you solve for the area of the footing. Once you got your area of the footing that satisfies this pressure, you go back here and now you take your factor reactions, right? Divide by the area of the footing that you found, and that becomes now the ultimate pressure applied in your footing. Okay, so this is your factor pressure applied to your footing, and this is the value we use to design the footing. All right? Okay. Let's start with the continuous footing, which is your strip footing, right? It's a wall right? And this is the easiest one, because what you're going to do really is design this portion here of the footing as simply a cantilever. Okay, so that's a cantilever area. So you have rebars going here at the bottom. So you have to assume this. Well, I cannot turn it around, right? But if you just imagine you're turning this all the way around, and this becomes the top and this becomes the bottom now, it's like having a wall supporting a slab, right? And you're putting your loads here because that's your soil, right? You're putting your loads, so it's like applying this vertical load in your slab, but going this way, right? And so you are bending this as a cantilever, going that way. Your tension side is this one, okay? So just imagine this flip around and this portion being like a slab, right? Sitting on top of a wall, right? So this becomes a cantilever slab, right? So that's basically what you're doing, all right? With the difference that the load that you apply here is the pressure from your soil. Right? Okay. So again, I mean, this is units, and this is per length. We're going to do this per length of wall. That's the only difference here. We're going to have the service loads times the unit of length, because we're going to multiply by 1 foot, right? So because this is a long wall, we take only 1 foot, like we did with this slab, right? Here we take 1 foot, we design 1 foot, and then we design per foot. Okay. All right. Divide by B and the unit of length. So really this cancels out. So really what it means is you got your load divided by B has to be less or equal than your allowable net pressure. Okay. But remember service loads, right? Then you need to find your design load, right? And that will be your factory structural loads, unit length, but that will be this way. So now you get your factor load. This is now the pressure that you use for design. This is the WU for design. Okay. This one right here is only to find the width that you need for this footing. Okay. So service loads to define the width. Once you found your width, you go back and you find your pressure. Okay. All right. Critical sections. This is the one we normally do, right? Concrete. Critical section at the face of the connection. All right. If you have a masonry, it will be halfway between the center line and the edge, which means at B/4. If this is B. If this is the thickness of the wall, then this is B/4. You have a steel beam with a plate, right? Again, this will be the distance from the edge of the flange here to the edge of the plate is E. Then it will be halfway of that distance. So E/2. That will be your critical distances. Okay. So for steel and masonry, the critical distances are not at the face of the connections. So be careful, because I could ask this in the final, right? Okay. All right. So for the strip footing, then all you're going to put is these bars going that way. Okay? So this is the wall, right? This is your strip footing, B, and you're going to put these bars. So it's like a slab, okay? At the spacing S. That's what you're going to do. Okay? Now there is of course other things that need to be done, but that's the basic concept for that. So normally you have your unit for loads, right? Your live load. Oh, I didn't change this. I need to change it. One of these I need to change. This one. Let's see if I can change it. I don't think I know why I didn't change it. Because it is a figure and I couldn't edit it. And, this is 11. Okay, this is 11. Not. So this is 11, not 15. Okay. So. I mean, I can delete it. I don't know if I even can delete it, but I would delete the whole thing. All right. So that's an 11. Okay, so that's the only difference. The 20 is okay. So we got this. We find our load, right? And since I gave you already the dimensions, so it was nice here. I gave you this 10, and there's a 2 already. So that became pretty easy. Then I found my pressure from the loads, and it will be 1.2, right, times the 11, not 15, 11, and 1.6 times my 20, right? And we divide by the area that would take this pressure, which is 10 feet, right, times this length. But remember, we're going to do it per foot, so we use 1 foot. Okay? So then this is my pressure per foot. Okay? Critical section at the face, right? So we're going to do that. We need to find a D value, right? We need to find a D value. So D will be H minus the cover minus D sub B. They're noise stirrups. So 24 inches, that's 2 feet. Cover for footings, this is going to be exposed here to dirt, cast probably on top of that dirt. So 3 inches of cover, right? And 1 inch for your bars. You say, well, wait a minute, what do you mean 1 inch? It wouldn't be half? No, because you had 2 layers. And so our D now, instead of going to the center line of this layer, we're going to go and find an average D that goes right between the 2 layers. So it will be 24 minus 3 minus 1 layer, which is 1 inch. Okay, so that's 20. So then you can use that D for both directions. Right? You get that. All right, so that's my VU 452. My critical distance, right? I need to find my VU here, right? So what I need to do now is I need to find, so now this QU, right, is the pressure being applied here at the bottom. Remember, think about a slab, right? Cantilever slab. So you cantilever slab, you turn it around, it will be a cantilever slab with the pressure being applied here that equals this value, and you are designing for the cantilever portion, right? Critical value here. So my shear will be the shear at the face minus the distance D, right? And so that's what we're doing here. Okay, so I'm going find my shear at the center line. That will be the 5 minus 6 inches to move it to the face, which is that one, half of the wall, and then minus my D, right, to find my BU at D, right? So I get my number here, 12.8 kips per foot. Right? Everything per foot because I'm doing per foot, right? So this is now my VU at D, okay, at the distance, the 28 inches from the face. Find my V sub C. Oh, now we need to use this tricky formula. Remember? Why? Because there are no stirrups, okay? So we had to use the tricky formula, same as slabs, right? The big difference, and this is one big difference, okay? Lambda S, 4 footings, we can use a 1. The code allows us to use a 1, regardless of what you got. I mean, you can use the actual, you can find your D and find your lambda S correction, like you did in the slabs, right? But now for footings, the code permits to use a 1, okay? Okay, so we need this rho W though. So what do? We haven't designed it yet. Okay, so we need to assume a value, and so what value are we going to assume? Right? For slabs, remember we're very conservative. We assume a number 4 at 12 inches, right? Because that's the minimum you can use. Because those slabs are small. I mean, you usually don't put a lot of steel. But in footings, you can put a lot more. Okay? And I mean, you can have that. I mean, from 8 to that. So I was thinking, well, you can use a 0.40 inches squared per foot of an average, right? Between 0.20 and 0.79. But I would say most footings, I mean, you're looking at on the high end. Okay? So I will go with the number 8 at 12. Okay? And so that's what I did, because otherwise you do the other one, it's going to be very conservative, and this year is not going to pass. Okay? And you're going to be increasing your depth of the footing when you don't need that. All right. So let's assume more on the high end. I mean, you want to be a little conservative, maybe use number 7s at 12 inches, okay? Or 6 at 12 inches, but don't go to number 4s. Okay? I will say, yeah. Number 8 at 12 works here, so we do that one. Is 1 foot. My D, remember, that's 20 inches. So I put in the formula. This one, as I said, it can be used as a 1. The code allows to use a 1. And there is the 1, and there is the A, 0.75, my F prime C. Per foot again, my D, they're giving me my value for phi B sub C. And this is greater than the BU, so we're good. Notice that if I put here 0.4, gosh, I mean, I will not make it, okay? I will not make it. I will be changing this D significantly, which when I don't need it. Okay? So in footings, try to be a little bit more on the high side. Okay, the footing depth is adequate. Now I'm going to take my moments. My moments, of course, are going to be now, remember, this is a cantilever, right? This is a slab. Looking, you turn it around, it looks like a slab in cantilever. And so your moment is critical at the face now, right? So it will be 5 feet right at the center minus half of the wall, right? That will be your distance. So there is this 10 feet, so we're over 2. That's the center point minus half of the wall. My distance is 4.5. So I find my moment, QU times L over 2, right? That's my L squared over 2. So I get my moment per foot. And I use my formulas for been using this all the time, right? So we get our area of steel. That doesn't change. Check minimums. Footings use the same minimum as the slab. Okay, same concept. So 0.52, that's my minimum. So my required value is a little bigger. So we're going to use that. Well, we're coming out now with number 7s. That's 0.60. We do the same as in slabs, right? So this is what we need. We're going to find out the values that we're having, right? And so here's the 0.60. We solve it. We get an S of 0.114, right? Something is right. What is not right? Oh, I know it's not right. This one. This is 0.57. So that's what is not right. Now, in the case of footings, there is no cracking control, so you don't have to use cracking control. Don't do that. Okay, there is no need for cracking control. So this will be okay, but now we're going to get more than 12. So 12 times 0.60 divided by 0.57. Oops, that didn't work. Okay, so that's 12.6. So let's say 12, right? And so we are going to put these guys at 12. Oh, that may change our shear issues. So since we're doing 0.60 at 12, so everything goes to 12. So now we got 0.60 really at 12, right? Yeah. So I wonder why that was there. Unless this value is wrong, I haven't checked that one. But 0.57, let's do that a quick check here just in case that one wrong. So it's 46 times 12 divided by 0.9 divided by 60 divided by 0.9 divided by 20. 0.57. Yeah. Well, that's an approximate value too. All right, so we get that. Check capacity, so we got that one, so same, that's my D sub T will be the same. C, we can find here the area, but I'm using this one now. because now this one is 0.60, and that's what we didn't do. So we get 0.60 times 60 divided by 0.85 divided by 4 divided by 12, and our value is 0.88. Okay. And so we find our C value, of course. That would be okay. 0.88. Oops. So the number is now 104. And that would be okay. I mean, this one is okay. That one would also be okay. So 104, 104. And we got 2013 minus 104 times 0.003 divided by 104. And that value is 0.055. So definitely satisfies ductility without any problems. All right, so AS maximum is satisfied, Phi factor is satisfied. Let's see what we're doing here now, because this one now we change it to 60 and this one to 0.88. So let's see the capacity is okay. So that may be the problem there. Okay, let's see. 20.13 minus 0.88 divided by 2 equals, okay, sorry, times 60 times 0.60 times 0.9, and that one is 638 pretty much. So 638 we divide now by 12 and we got 53.2, so we're still good. Okay, 53.2. And so number 7 is at 12 inches works, and we be okay. Now we do maximum spacing the same as we did with slabs. So we satisfy that. So that one is also satisfied. And next we have to do the temperature and shrinkage value. So we do the same formula, 1224, that one. And here, yep, pretty much number 7 is at 12.2. So would be that, same as before. Is satisfied is maximum. And let's recheck that's here. Now I think we are going to be bad. Well, let's check it out. The new D value is 2013. And so let's check out that one. I think this one is going to cause problems. Yeah, now with this new formula, I mean, that shear becomes so critical that you need to recheck your assumption. All right, so 0.60 divided by 12 divided by 20.13, and that has to be raised to the 1/3. Right? Yeah, that's very low. Times 8 times 0.75 times 12 times 20.13 times the square root of 4,000. 12.4. Okay, well, yeah, close. 12,414. 12,414. So 12.4. So you're happy. You can say close. Close. Okay. So we got it pretty close. Now we know that the number 7 is at 10, right? Number 7 is at 10 inches, which I had before, works. So that's another possibility. This is quite slow. So we increase that one by simply changing that. So here I'm going to put in, so that one will be okay. Now you don't like that, so you want to be okay. So we know that number 7 is at 12 work for our purpose of moments. We can change number 7s at 12 to number 7s at 10 inches. Okay. And then that definitely works for your shear. Okay. So because of shear, then we will be changing that to number 7 is at 10. And so if I do, you will have to do this equation again with number 7 is at 12, which is now copy. And let's put it here so you have it, right? Oops, that doesn't look very good. Let's see if it works here. Okay. But now we're going to put this number 7 is at 12, which this one is now 0.72. Right? Number 7 is at 12. No, you don't remember how to get that. Remember, I'll go here. Well, let me finish this one and I'll show you. Okay. So we have then 0.72 now divided by 12 divided by 20.13. We're going to raise that to the 1/3. Right. And we multiply times 8 times 0.75 times 12 times 2013 times the square root of 4,000. And so now we get 13,192. See, 13,192. So let's say 13.2. 13.2, and definitely now we are greater than the shear VU, right? And so that satisfies the shear. You are concerned about that. That's how you fix it. All right. Okay. So some of you will say, well, how you get this 0.72? Remember here, right? So we go back here, right? And now you are providing, right? Remember, you're providing. So you're putting now 0.60 at 10 inches, and you need to find what this value is at 12, right? So that's what you're doing. Okay? The area provided, right? Which will be 0.60 at 10. This will be a 10. This will be 12. This is what you're finding. This will be the new value. That will be your AS provided. So 0.60, 10, 12. And then you solve for this one, which gives you 0.72. Okay. Okay, so that's your 0.72. And so that solves the problem. And so there they are. Okay. So your shrinkage bars remains on number 7 at 12. But your main bar, which is here at the bottom, right, is number 7 at 10. So make sure you know where to place it. Okay? Because if I ask in the exam, that will be, you need to show me where. Don't put it here on the top, don't put it in the middle, okay? So just make sure you put it in the bottom, all right? Okay, so that then works, and some people like to put also some shrinkage bars right here on the top, like longitudinal bars, right? Yeah, to control some cracking here on the top sometimes because of temperature shrinkage. That depends. All right, so that is your strip footing. Okay? That's the simplest footing you ever going to have, is designing the footing for a wall. The next one, second place on being the simplest, is the isolated footing. Okay? And the problem with this one is that when you look at shear, now you have one-way action and two-way action shear. Okay? Now you can have rectangular footings or square footings. You say for your project, square footing, please don't do rectangular. Okay. Actually, I erased the rectangular part from this one. The one that you're going to get doesn't have the rectangular, so you don't. So you're doing rectangular because you're copying from some place else. Okay. Because I erased it. You don't have it here. Okay. Now, normally we don't put shear reinforcement, right? But because of that new formula, right? Notice that new formula in the code, right? Oh gosh, I mean, that new formula. Now, the one-way shear is more critical than the two-way shear. It's completely backwards, but it used to be, right? Hopefully they will change that formula. But for now, that's what they have, and is creating a lot of headaches. So how do you estimate your footing thickness? Here you give you an idea. Idea, okay? It's a guess. Don't hold me down to this, okay? This is just you start with something, then you improve it. You make the changes, so you make it work, right? But you have to start with something. So either your footing will be equal to your column width or 1.6 your column width. Usually more than 12 inches, okay? You never had that. It's 12 inches minimum usually, most of the time. So you have an 18-inch column, you're looking at 18 inches or 24 inches, right? Something like that, yeah? Approximately. Yeah? So, but that's what you want to do. That's just to start. Mm-hmm. There are other formulas in your geotechnical books for foundations. You can find those, okay? And so you can do those. And 1210. No, 1210 is another reference. There's another book. That's Coduto's. Coduto also has a good foundation book. Bowles here is an old book, but it's very comprehensive. I mean, in terms of foundation, this is very comprehensive. Even at the time that was published, he was already using some software. I mean, not as sophisticated as the one we have now, but at least some software in there. Okay? But very comprehensive, this one right here. Okay? Mm-hmm. So you have better formulas if you want really to find a precise value, a better thing. Yeah, you can do that. Okay. So what is the problem with the shear? Okay, the problem with the shear is that now you have this two-way action shear. We haven't seen this before. Okay, and so for that, let me see if I can get that here. Because this first time I think you guys are seeing this. And see a good one here. I'm looking. I'll put it in a minute. I want to see a real thing. Okay, well, let's look at this. Kind of. Mm-hmm. Kind of. not that great, but okay. So here is some. So this one right here, you can see the column, right? This goes through, okay? And that's why you got a double, so shear in all directions, right? Shear problem here, shear problem here. So that's what we have. The model, right? This is the model right here. So we're assuming that the column is taking a piece of concrete and is taking it through and pushing it down in this case, right? For the case of this. No? This concept was developed mainly for slabs, but then it's being transferred to footings, right? And so really what is happening is something like this, right? In a slab, the slab will fall down because the column will just punch through. Right? But we're applying, remember, backwards. So we're seeing the slab as our footing, right? And so now the column is going to punch through, yeah, in there, right? So there is that possibility. Of course, there is the soil, and so it's less of a hazard, right? Because this one is going into air, so that's why the slab fails, because in slabs, there is nothing else, right? But in the case of the footing, it is punching through, but going to the soil, so it's kind of not that bad, but still, there is a punching shear effect. Let me see, there is another one. It's difficult to see one of these because normally when it happens, I mean, they're buried, and you need to excavate and try to get it. I don't see any real failures of those there. No, okay, but that's the whole idea. So the column could punch through that footing, and therefore we need to protect it. All right, and that happens not at the distance d. So we consider this again the point of critical. Okay, and not this will not be d anymore. This will be d over 2 now. Okay? So that's what we call a punching shear failure. Critical distance at d over 2. And the other thing that you had to look at, let's see, we go back. Oops. Yeah, well, this is not bad. If we look at this again, right? We look at this one, right? This happens in this perimeter, right? So the area that is carrying the shear, right, by equilibrium, right? This force is coming down. You need to have shear forces here on these faces, right? Going the opposite, right, to balance this. When this is greater than the shear forces that you have along the faces here, right, then you got a failure. And so the shear goes then along all this area. So that means the perimeter is this. Multiplied by the d value, give you the area. Okay? So your total shear area is the perimeter, right, multiplied by d. The perimeter is what we call B naught. Okay? And d, of course, is what you already know what d is, right? But the perimeter is then this length right here, because the shear on each of these faces, right, has to add up to the forces in order to maintain equilibrium. All right? And so that's the B naught that we talk about here, that perimeter. Okay? In there. Good. So again, I mean, you need to satisfy this. So that's no changes there. Normally, we use the concrete only because we don't have stirrups, but you could put stirrups. And then you had to follow the same design as shear with the stirrups. Okay? So you may have either one wide beam action, which is your one-way shear. So wide beam action, that's one-way shear, another term for it. And then the one we just described, which is the two-way action, which is your punching shear failure. Okay? So we had two shears, right? Two types of behaviors. The wide beam action, which is your one-way shear, the one that we learned. And now we got the punching shear, which is the same as the two-way action. All right, for the wide beam action, we know that we need to use this formula, right? And as I said, lambda S, as we did for the wall, the code in section 13262. Let's double check that. I'll tell us too we don't need to use that value. Oops, I think I closed my code. No, let's see. Code right here. Okay, here is the code. So 13 is you have foundations, right? And so lots of little things and foundations here. 13262 right here. 13262. Okay, what is this thing? Okay, there it is. Barely here. Okay. All right. So for one-way shallow foundations or two-way isolated footings or two-way combined footings and mud foundations, right? Then it is permissible to neglect the size effect factor. Okay. So we can do that. Okay, for one-way shear and for two-way shear, we can neglect it. Right? And we're going to take advantage of that because, again, if you don't use it, you will have lots of problems with shear. All right, so take advantage of it. So that means then that this value is going to be a 1, right? The lambda is. The two-way action has different formulas, not just one. All right, 3 formulas, and we're going to pick the lowest. Usually this one. Okay, usually this one. It has the lambda s too, but again, we can ignore it, right? The other problem that we have here is that the new code 3.18.19 is giving you this in terms of stresses. This is not your capital VC, right? No, this is not a force. This is a stress. Okay, so be careful. So this is now in terms of stresses. That's how the formula is ended. So what is the beta? Beta is simply the ratio of the long side to the short side of a column in this case. Okay? It can be also the long side or short side of a footing or a wall. So beta is always long side or short side of a member. Okay? Alpha S is a special coefficient that depends on where your column is sit. Okay. For most footings, your column is right in the center of the footing. Right? But there could be special cases where it's not. Right? And B naught, I already explained what B naught is, right? That's the critical perimeter, right? So that's very important. So we'll come back to this thing. And that is taken at a distance d over 2. So to find the critical perimeter, you measure d over 2 from the face of your column, right? In both directions. And then that defines where your B naught is going to be measured. Okay? And that's what is shown here. Okay? So you have this column, one-way shear, you do D in this direction, you also have to check the shear in this direction. So that's what I said. Don't do a rectangular column because you had to design twice. Okay, it's double work because you had to design your shear, your one-way shear this way, your one-way shear that way, and on top of that, you had to design your two-way shear. All right. So don't do rectangular sections. All right. Now so this is the generic case, right? So we measure d over 2, d over 2, d over 2, d over 2, right? And then those lines that are going to be there perpendicular to those d over 2s define the perimeter B naught. Okay? So for one-way shear, we use D, and for two-way shear, we use d over 2. Okay? So different critical sections. Okay? So you have some weird thing like this. I mean, the code allows you to do that. So you kind of join an imaginary line here. You measure d over 2, and then you get that perimeter like that. Always perpendicular here. In reality, here should also be d over 2, so you kind of round it. But no, we don't do that. So just keep it straight. Okay. So at the end then, if you have a rectangular section, right? So this value right here, right? This distance is going to be the column dimension here, C2 plus D over 2 and plus D over 2. So it's C2 plus D, right? You go in this direction, C1 plus D over 2 plus D over 2, that's C1 plus D, right? And you have 1 and 2 and 1 and 2, right? So then your perimeter, your B naught, becomes 2 times C1 plus D plus 2 times C2 plus D. Now, you have a square column, right? C1 and C2 are the same, and everything changes to this, right? Now you have a circular one, you can use this formula. So either this one or that one, okay? But don't do rectangular. Okay? All right, here is the alpha. Right? Alpha S 40, column right in the middle. You can have this one. Remember that perimeter line? You may have to put a column inside your perimeter line and creates this issue. So now notice that your B naught is only 3 sides. Okay? Only 3 sides. Now you have an edge here, your column is a little bit inside. It's still a stereo edge, but now you have another face because you left a space here. Okay? This one right here is a corner one, very rare. Okay? Because in these cases, normally what you do is you join this with another column and make a combined footing. Okay? The same with this one. I can join this one with another one, make a combined footing to avoid that eccentricity. Okay? So the one we're going to see is this one, okay? The most common one. Okay, the other problem is that as your sections, right, become rectangular in shape, then the behavior starts changing, and then your strain capacity, right, changes also with this B naught divided by D. Okay? And that's why there is that formula, right? Because it's reduced at one time. So you look at these, right, formulas, notice that in order for this one to be smaller than the 4 that you got here, this one has to be greater than 2. So you have to have a rectangular section that is more than 2-to-1 ratio. Then this one controls. Otherwise, this is going to be bigger than 4. The same here, but it's a little difficult because it's this D over B naught that again there. Okay? So the shear strength is inversely proportional to the B naught D ratio. Okay? So don't forget that for those quick questions in the final, right? So shear strength capacity decreases as the ratio B naught to D increases, right? So they're inversely proportional. Okay. And also as you increase, you make your rectangular columns a ratio greater than 2-to-1, your shear strength also decreases. Okay. All right. So after you find your B naught, right? So I show you already how to find it. You find your B naught. Then how do you change your lowercase v sub c into a VC that we normally use, right? We multiply by B naught D. And that makes it now the V sub c that we normally use. All right. Flexural strength. This we already done. We need to have though reinforcement in both directions. Okay. So it's like designing bending in one direction, then you have to design bending in the other direction. Okay. So you have now if your footing is rectangular, then there are special requirements on how to distribute the bars. So that's what I said, don't do rectangular footings, okay? Because there's special requirements I'm not going to show you here. Okay? All right, what is the minimum the minimum is same as slabs, so we got that one, right? And here is a regular square footing. So notice that you design in one direction, you already got the other direction. It's the same. Okay? But if you do a rectangular footing, notice that the rebars going in this direction is not the same as the rebars going in this direction. They are different spacings, right? And so it's more work. So don't do rectangular footings, all right, for now. When you learn them, you can do it, but not now. Spacing the same as slabs, 3/8 or 18 inches. Other thing that you have to worry about it is because you're putting a column into this footing, then at the base of the column, you need to make sure that the column does not crash, right? And so we need to look at the bearing capacity of the column. And there is a bearing formula. So this is the bearing capacity of a column. And is given in your ACI, section 22A32. So, now I don't have my code. Oh. Yeah, so that would be a special chapter that we haven't seen yet. Right, and so let's make sure that we got it right. So, what happened to my code? Okay, code. Okay, here's the code. All right, 22. So we're looking at 22.832. So remember, anything about designing formulas are here. The ones that at least the code is giving you. Okay. Okay. So 22.832. So here are the formulas. Okay. There is the one I'm giving you, this one. Okay. So this is the first one right here. And then you have this one right here, which is the supporting surface. That will be your footing, right? So the footing has to go through this, all right? So it has two values that we need to check. So we're going to do that. So this is the one with the column. So that's based on the area of the column. So this is the area of the column. Okay. And then the footing has two formulas, right? And this area 2 is the area, not exactly the area of the footing, but is the area of a truncated pyramid, okay? Or cone, you're doing circular, right? With the slopes of 2 horizontal, 1 vertical. And this is very important because a lot of people use the area of the footing, and sometimes it's not, okay? However, in most cases, I mean, this one controls. I mean, it's very hard not to have this one controlling. Okay? You can change this one by saying, oh, I'm going to use this symbol here, kind of weird, right? And I say that symbol represents one of these two, whichever is the smallest, and put it there, and that becomes the same formula. Okay? But that's not important here. So what is this truncated pyramid? Let's see, we have some right here. Okay, there it is, 45 degrees, nice, right? So we're going 45 degrees, right? But we need to go 2 horizontal, 1 vertical. And the moment you hit the wall, right, then that's the maximum you can use. So in this case, you can use the full area of your footing because this one is getting to the here, this one will get to the same point. So that means your truncated area, right, matches the footing. This one, though, is different. You go 2, 1. Now, this one hits the wall first. This one doesn't, but you cannot take it down, okay? So it has to stop at the same level. So now your area is smaller than the area of the footing. Okay? So whatever is the shortest value that hits the edge, that's the one you had to use. Okay? So here's another one, for example, right? This is a rectangular footing. So if you go in this direction, you're going to hit the wall faster than you go in this direction, right? So in this direction, you're going to hit the wall at this point, which is H1. So that means that when you go in this other direction, you have to stop at H1. And so that becomes your area now. That's what I said, is whatever you hit first, that controls your area. Okay? And so notice again, the area of the foundation using that formula is not the area of the footing, is this area right here, which is different. Okay? So be careful then with that area too, because it's not the same as the area of the footing. Well, again, a good thing to ask for a quick question, right? Okay, the minimum area of bars that you need to pass through the column into the footing is given by this formula. Okay, and that's given in ACI section 16341. Oh, this is kind of messy now, right? Going to 13, 22, 25, 16, right? So we're going to different chapters now. But chapter 16 is the connection chapter, right? That's why. Connections, right? So 16341. Let's see. Okay, right here. Right? So this is what you need to satisfy. Okay? At the interface, that's where you're crossing between a column or a pedestal, a column or a footing, a pedestal or a footing, any transition like that, right? You have this minimum amount that you need to do. All right? Okay. You do not satisfy that, if the PU is greater than your bearing, right? Then this is why you find the area required. What is the actual number of bars that need to go through? PU minus your bearing divided by the strength of the bars. It has to be greater than this minimum, because this represents the minimum that you can put. Right? If this value is less, then you use the minimum. Okay? And those bars are what we call the dowels. Okay? These are the dowels. For some of you that have made the visit to the construction and have seen some columns, those are the bars that kind of stick out sometimes. Yeah? They're from the footing up. Those are the ones. Now you can, in the case of the dowels, you can have larger sizes than the column bars. You can do that, but usually no more than one size larger. Mm-hmm. This kind of practice. Mm-hmm. Now, if you have number 14s or number 18s in compressions, your dowels cannot be more than 11 bar. So that's an exception there. So 11 to 14, 11 to 18. Okay? Very important. And again, that one is in 16354. Okay? And so if we go here, right, all footings, compression lap splices of number 14 and number 18 bars that are in compression for all factor load combinations shall be permitted in accordance with 25553. So now you go to 25553, right? And 25553 tells you that number 14 and 11 bars to number 11 or smaller shall be permitted. Okay? So that's where you have it. Okay? So that's the exception to that. Otherwise, no more than a one size larger to do your dowels. The dowels, of course, will extend right into the footing. And two problems. You need to define the splice length, right? The splice length. And you need to define your anchorage length right here, right? And so development lengths are required to be checked, and splice lengths are required to be checked. So here we're going to use what we learned in the previous chapter. So here's the example. And again, I mean, I think I changed the loads, but I couldn't change the figure because this figure was done, I don't know what we used for this figure at one time. And this was copied from a MathCAD solution. And so that's kind of, sometimes you have some weird numbers. I noticed that. But I couldn't change this. But the values are 345 now and 178. So 345 and 178 coming down into this. Okay. So 345, 178. So this one has been changed. Okay. You got the column width 20 in there, right? And then you got 2 feet here, 6 inches of slab, right? That adds the weight that we need to consider. Okay. And so we got the dimensions. Here is that weird rectangular section that you don't want to do that, really. You want to make it square because it's a lot easier, right? In there. You have a 6-inch floor slab. This is what I gave you in your project. This is the one where you're getting confused and you were trying to use it for your floors. No, this is your slab that is in your floor, in your first floor, okay? There is the pressures that I gave you too, all right, for your project. In this case, I'm saying that the top of the footing is going to be 2.5 feet below the floor slab. You can make the same assumption if you want in your project. Now here, though, you're going to put the loads that you found for the first floor. Remember you had these first floor loads that we were not using? Now they become important because you had to transfer that here. It will be subtracting from your gross value to make a net value, right? And so that's what we have that. Then I also gave you the unit weight of the soil because you need to add this weight. Now you can add all this. Normally we ignore this column and we say all this is weight of soil. Okay. All right, so column dimensions, compressive, see all this set up like MathCAD. Again, these loads have been changed, and this one I should be able to change, I think. Let me see. 345, 178. Yeah, so I can change this one. All right, so these are the real loads we're using. The allowable is 3,500. Soil on top 2 feet, slab thickness 6. Floor loading 75 PSF. Okay. Soil pressure. So we're going to find that, right? First, we need to check the height, right? We need the height for the footing, even though I think here it shows that already, or no? No, I didn't show it. Okay, so we do this magic formula. Remember I showed you, right? 20, 32. Oh, I just pick a number, 28. Okay. This is a guess. Remember, it needs to be checked for your shear, it needs to be checked for your moment, all that, right? If it doesn't work, you change it, but you are close. Okay? Now you know what to do. So I'm going to find the footing weight. So this is the weight of the footing, gamma of the concrete, right? Because of the footing. The height is 28. That gives me this much pressure from the footing. The weight of the soil, 2 feet of soil, gamma of the soil, 200. Again, as I said, we are ignoring the width of the column. So we're saying all this is soil. Okay. Next, we're going to the slab weight, 150 times 0.5, 6 inches. That gives me the weight of the slab. Again, we are assuming that slab goes all the way through, right? So that's little things in there. So we got those weights. Floor loading that was given. So we got 75. Yeah, in your case, I think you have what? Some other pressure. You have like 100, right? Yeah, for your project. So you got that. So the net allowable, then it will be my allow that was given, right? Minus all these uniform loads. So I'm going to take all those out, and then it becomes a net value of 2,800. This net value has to carry my loads from the column. So my loads for the columns are these. So I divide by my net, that gives me my area that I need for the footing. Since I'm going to make this a square footing, I get about 14 feet. So I'm going to have a 14 feet by 14 feet square footing to carry my load. Okay. So the only purpose then of factoring things is to be able to find this area. When you got this area, you factor your loads again by, normally you already have them factored, right? And you divide by the area and they give you the ultimate pressure. This is the pressure that's being applied in the footing to create your bending and shear values. Okay. Of course, loading 1.4 doesn't control, and that's why it has not been considered. So here is then that with the pressure. Okay. So again, you can turn this around and you can look at like it's a slab on top of a column, and this is your reaction, right? You can look at it that way. All right. So we're going to design then for this, and because it's a square, right, the worst length dimension, right, is going to be this one, right, because this is 14. So it gives me the longest value and therefore the longest bending. On this direction is a little shorter because this is 20, right? And so I'm going to design this way, and then I'm going to use the same on the other direction. But they're close, right? This is what I guess, 28, right? And so now we go and start checking. We find a D value, approximate value. We're going to assume number 8 bars. Typical cover is 3 inches for this. And usually you have 2 double layers because, you have double layers because you're going to put bars in this direction and bars in this direction, okay? And so you have double layers. And so our D then is a D average. Okay? So it's H minus the cover minus the diameter of 1 bar. Okay? Not half of the bar, but 1 full bar because we're doing the average, right between the 2 layers. And so they give me 24. This one, right, is step 2, right? And it always was a step 2 because the two-way shear used to be the most critical thing you have for these footings. But now with the change of the new formula for one-way shear, two-way shear is going smooth. No problems, all right? So, what is the two-way shear? We need to find the perimeter, right? But at a distance d over 2, right? So how do we find that perimeter? Well, so we take that one, right? And remember your C dimension plus d over 2 plus d over 2 on both sides, so that gives you d. And then the other dimension is your other dimension of the column plus d over 2 plus d over 2, so that gives you the d again. You multiply those 2 dimensions, that gives you an area, right? That's the area of the perimeter. Okay. So what I'm doing here, let me see if you can do this. All right, so there it is. So here is your footing, right? And I'm subtracting this area, which is the perimeter critical, right, at the distance d over 2. Okay. And so what I'm going to say then is the load applied on this shaded area, right, is the shear that needs to be transferred along these faces. Okay. Okay. So remember this breaks, right? This is the area that is going to fall, right? The shaded area. And so that load has to be transferred through these faces right here. Okay. And so that's why my area, my shaded area, is B squared minus the area of that perimeter. Okay. So B squared, which is this area, minus the area of the critical perimeter. That gives me the shaded area. Okay. So the shaded area then is this value, right? Excuse me, this is my perimeter area, and then I can find my shaded area by doing the subtraction, multiplied by the pressure, the pressure from the soil, right, that we found here, remember, after factoring. So that was the load that's being applied to my footing now. So multiply by that, so load times area, that gives me the total force, that's the total force that's being applied on the shaded area. So that becomes my shear force that has to go through all these phases. So that gives me that number. Then I'm going to find my perimeter, right? So my perimeter, again, you are going to add this plus that plus that plus that, right? So you're adding that gives me my perimeter. I'm going to find my beta, so you got rectangular column. I don't know why you do rectangular column, right? It's just more work. So you have a beta now of 1.42. Should have been, you could have done a 1, right? But there it is. Center column, so that's a 40. My Landau normal weight concrete. Remember, this can be ignored. Good thing. I mean, gosh, that would have been killer. Okay, so we can ignore that one. 13262, right? And we find our values. I multiply by B naught D, so now the stresses now became forces, V sub C, okay? So there are my three values. I pick the lowest. As I say, usually that one governs, and that's what it is, okay? So you are rushing in your exam, right? You don't have time to check these other two formulas. You can say, I'm assuming that this is going to control, but that's the normal case, and I'm going to continue with that value, right? And then you say a couple of calculations here. But these need to be checked. Especially, remember, this one is easy to discard, because you have a square column, this is gone. That would be a 6, more than 4 already. This one a little bit more difficult, but you have a center one, yeah, normally it's going to be also high. Okay, so 90% chances that's going to be high. So that means this one controls. All right, good. All right, so I got then this value multiplied by my phi factor of shear, 0.75, is bigger than my VU. Great, pass two-way shear. My height is good. Now I have to do one-way shear. One-way shear. Remember, we're going to go into the longest length that we got because this is rectangular. If it was a square, it doesn't matter which direction you do it. So I need to find my critical distance for one-way shear. That one we know is a D value, right? It's from the face, a distance D. That's my critical section for shear. So I need to find this loaded area. So it will be my pressure times this loaded area, right? Now, don't ask me for formulas for LV. I mean, I show formulas here in the calculation, but you don't need that, okay? We are finding this value, which simply is half of the footing minus half of the column minus D. That gives you that value, okay? So I think I don't have, maybe I had it. You got some formulas for footings, so maybe I was nice and I gave you all that, but you don't need those formulas, okay? Those are for those guys that are copying, that I noticed you were copying in the exam. There was an error in one solution. You just went through that error, I mean, like nothing. I mean, just did the same thing step by step without even thinking what you were doing. So, yeah, for those guys that probably want to do that, yeah, you need a formula. Here's the formula, okay? But you don't need really a formula. All you're finding is the value of the critical distance D. And the shaded area becomes your area that you're looking for. So that multiplied by the B, right? This distance multiplied by the B give you the shaded area. Shaded area multiplied by your load give you your force. That is your total shear that is being applied along this line. Right? So there it is. Pressure times area, force. Okay, that's my VU. All right. Yeah, let's double here. This is for MathCAD. See MathCAD, that one, you kind of copy the same thing. All right. So B there, your BW, 14 feet. Because now, right, you're going to design, it's like you are designing now for a beam in cantilever, because this is your cantilever section, right? Cantilever is out that way. But it's like a beam that has a width equal to 14, right? And so that's why the BW is equal to 14 feet. because you are designing for this whole thing. Okay? So like this whole thing is in cantilever, and that's why your BW is 14 feet. That's your B. Okay? So find the VC now one way. Now here's the formula here. That's the killer formula. So assume number 8 bars at 12 inches. All right. So I get that one. As I said, got in the high value. Otherwise, you do low values, you are going to end up with a footing that is 4 feet thick. I mean, that's way too much. All right. So number 8 at 12. So that gives me 302 now. 0.75. Oh, this value is 227. Is greater than the 220. So we're good. All right. 28 inches then is still okay for my height. Now I'm going to design for bending, right? And bending again from the face of the column. That's your bending, right? Again, how do you find this value? Half of the footing minus half of the column in that direction. That gives you the value, right? Okay, so there's the bending. So that's your cantilever beam, right? Remember, the cantilever beam has a width of B, right? Okay. So length again, here it is. So B minus 0.5. So that gives you that number. So you don't need the formula. Remember, it's half of your footing minus half of your column. That gives you your length. Find the moment, right? And the moment, remember, is what? WU L squared over 2. Okay, there is the L squared divided by 2, right? And this is your W. You're multiplying your Q net because it's a pressure. You're multiplying by B to make it a uniform load, right? And so this becomes now a W. So W times L squared divided by 2. So cantilever moment. So that's your moment. And from here, I mean, you know how to do this. Remember that your B is 14. That's all you need to remember. Okay? So we apply the same formulas. Because I was using MathCAD, I was able to solve the quadratic equations, so I used this formula to solve for AS instead of doing the two-step approach, right? So yeah, when you have that tool, you can use this one. It's neat. I mean, you can do it. All right, so that gives me my area. Check my minimum. Again, my B, remember this B here is your full B of the footing, because you're not descending per foot, you're descending for the whole width. Okay, so 847. So again, this is my MathCAD, right? I need to select the value. So you do the MathCAD here, it picks up the value, and it gives you the value that controls, which is the 976. So I went and looked, and I said, okay, 24 number 6s will give me 1056, which is more than that, and that satisfies this. My maximum spacing, 84, 18. So now I look at my spacing, right? And I go B minus 2 times my cover minus 2 times half of the diameter of the bars. Remember, there are no stirrups, so you go from the, let me go to the end here, right? Oops. Okay, so we are finding that you're going to subtract, right, all the way to half of the bar, right? And then you're going to find your center to center and your spacing, right? But you need to subtract your cover, half of the bar, right, to get there. So that's what we're doing. We're doing on both sides, left and right, right? And so when we do that, left and right, then you get 2 covers and 2 half diameters divided by n minus 1. That gives me a spacing of 7. So you're putting your bars at about 7 inches. Okay? Your S maximum is 18, so you're good. Okay? So now I need to find my strength, so my ductility, remember, so I'm going to do that. Check for my ductility. Beta 1 is 0.85. Let me check that, because I think I made a change to make it pass. Because that shear was critical. Yeah, see, I did 4,500. That's what I thought. So my beta 1 then is not 0.85, is 0.825, right? Because we are using 4.5. All right, and so that changes here. And so we got some changes. I mean, these are not going to affect the final design, but it's a change. So it's 1, 3, 4, 4. Compression straight limit, D sub C, that's the same. So that doesn't change. And so now here, this one changes. Okay. Notice that this got lots of ductility. So ductility, usually you have lots of it. So it's like this lapse. I mean, you got lots of ductility. Right. So 24.625 minus 1.344 times 0.203 divided by 1.344 equals 0.052. All right, and so not much of a difference, but ductility is great. So I satisfy A is maximum, my phi factor is 0.9, and so all this then is good, and I can find my moments, right, and check. This value is what do we say? A value. Oh, that one is the same. 1. Okay, so that one doesn't change. Okay. So we're good. That one is good. So it doesn't change. We got that satisfied moment. Okay. And so with that, then I got my moments. Okay. So that's my design here. Right. When I put in my bars, approximately at 7 inches. Right. Number 6 is both directions. I didn't do the direction because the direction has less length. So I'm okay on that direction. All right. I already checked that. So that's the nice about having square footing. All right. Otherwise, you need to design the other direction. More work. It's double this number of pages. All right. Okay. Now I need to recheck this one-way shear because that's critical. Okay. That's critical now. You had to recheck it. Okay. Don't forget to recheck it. Please don't forget to recheck it. Okay? So I put 1056. That's my total area. Total my 24 bars. My B is the 14 feet. Okay. And my D is the new value that I found. Okay. So that gives me a raw W like this. I put it in my formula, find my value. Remember the B is the fold width, 14. Give me that, multiply, 221.8. I barely make it, right? I think it's 20 and 20 is my BU. So barely made it, right? So we did that. So one-way shear is now super critical for footings, all right? Oh, you said we're done. No, I wish we're done. No. Now we need to go into the other stuff. Now we need to make sure what? Do you have enough length to put these bars? Development length, right? We need to have the splices. We need to have the bearings. So we still need to check those. So development length, make sure that we have that. How much do we have available? Critical from the face of the column. So we find B minus the dimension of the column controlling divided by 2. You look at the smallest one. In this case, you look at the smallest one because that's the smallest distance you had to put your bars, right? Minus the cover, that means you only have 71 inches. Okay. So we're going to find our development length. Remember this little formula here, right? So we need to find all these guys and that. And so that's what we're doing here. Okay. So I find my C sub B. The spacing was like about 7, so it's a 3.5, half of that. Cover, 3 inches minus D sub B over 2. Same thing on the other side. So these are then my two values in there. And my transfer value, we can assume 0 because we don't have any stirrups, right? Check it here. Value controlling is 2.5, so we're going to use 2.5 here. The only thing we're having is we're using number 6 bars, so that one should be a 0.8. Other than that, all these are 1s, right? And so we go and we put in the formula, and we get 17 inches greater than 12. I mean, 17 inches is very small compared to the 71. So definitely we have enough length to put these bars. Okay. Bearing. Phi factor for bearing, 0.65. Area of the column is C1, C2. That's your area 1. So I found my bearing value, then 0.65, 0.85. So which one did I change? I think I changed the whole thing. Yeah, I had to change the whole thing. Usually you have, it is more common to have a higher column strength than to have a higher footing strength, right? And so I think I'm using only one F prime C, and I don't know if I change it here on the top. Should I have changed it? I changed here. So both concrete column and footing, so both are equal. And so that one, could I change it? Ah, great. So it's 4.5. Yeah, I had to make this change because the shear was not passing the 4 anymore. So I had to do that. That's what I say, one-way shear is critical now. Mm-hmm. All right, so with that, then that means that my column is the same, 4.5. And how about here? Did we do this one right? Yeah. I think we corrected that one. How about here? Yeah. All right. So now we have a 4.5 here. So 4.5. So then that value is approximately, what, 618.8 divided by 4 times 4.5. So you're looking at a 696.2. 696.2. So this is because of MathCAD. 696.2. Right? Actually, you don't even need it. I don't need it. MathCAD. So the B in the column is 696.2. All right. So we got it. Now we need to do the one for the footing, right? So I need to find the area, right? B1. So we're going to find those. So B1, B2s are my two values that are being here checked, right? So here is my B2, and here is my other one, the other one B1, right? So the one that is going to control is the smallest one, right? And so the smallest one is going to control, and that is your 11. In this case, it got down. In this case, it controls here. It goes down all the way to the bottom. It doesn't even get here. So that's another case where your slope will take you down, but you get to the bottom of the footing rather than to the walls. So then the width of the footing is not your area anymore. It's this one right here. Okay? And since you're going to the bottom now, you have this value here, and you got a different value on the side because of the different column dimensions. And so that's why we got two values, two different values. Here, this is the 11, and this is the other one. Okay? Because again, you're going 2 to 1, and you're hitting the bottom of the footing faster than hitting the walls of the footing. Okay? And so that's your area. So area 2 then is B1 times B2. Mhm. And that's this one. You multiply divided by the area of the column. This is your area of your column. Now this value is always pretty big. Okay, so 2 is going to control, and since this is the same as your footing, right? When you multiply by it's going to be the same as your column. This part right here is the same as your column. You multiply by 2 is double already. So the footings rarely control, as I said, unless the strength is a lot bigger. Okay? So between the two values, you pick the smallest, and we change this one, right? That one is now is 696.2. Oh, that means we should have changed the other one too, right? Yeah, we should have changed the other one too. So we need to change this one too. 4.5 and this one, right? Okay. What is it, in 696.2? Okay, so we got that one. And so we need to change this one, the other one too. Because of that, so that's 1392.3. Oh, this little change is going to make me work here. 1392.3. Okay. 1392.3 and 1392.3. All right, so that one is there. And of course, we're going to pick the smallest, and so the column controls, right? So your column value that we found controls, so that one controls. And see what changes we got here. Find my factor load. I don't think I changed this one. So let's go here. Controlling value 696.2. This one now has to change because I copied this from that MathCAD, but I changed the loads, right? And our loads were changed to what? 345 and 178. Yeah, 345, 178. So I think we already found this value. So 1.2 times 345 plus 1.6 times 178, right? So 1.2 so 698.8. 698.8. This one is 696.2. Still below. There's a 698.8. And so dowels will be needed. So we still need the dowels, right? And even if you don't need it, I mean, you have to look for minimums, right? And so we are going to find that. Going back to this page. Oh, still development length. Oh yeah, we did development length already. So we did development length, and we're doing the bearing. Okay. So I have that. This one changes. Now it's going to be a lot less. It's going to be less than the minimum, bro. Let's see how much we get. So this value is now 698. 698.8. Okay, so minus 619. So that would be that divided by 0.65 and by 60, 205. So still, oh, but 205, yeah, I don't have value. Okay, right here there is a value. 205. Okay, so 205, this is the minimum. You have to check your minimum, and the 205 controls over the minimum. So 205 controls over the minimum. So use $6 number 7. That will give you 306. It's more than the 205. So we are good. Oops. Okay. Yeah. So now we need to find the development length for Dowers, LF. So now what we're doing here is, oops, we go here. We have that drawing. Where is that drawing? Oh, right here. So now we need to find this LF. Okay? Make sure that this length is enough to develop your bars in compression. So we're assuming compression bars. If it's a tension bar, you have a tension bar, you need to make sure that you have enough length to put a tension bar here. Now, the hooks that you see here do not work in compression, but they work in tension, but not in compression. So in compression, you will have to subtract that. This is more like you bend it like that, so the bars will not punch through. Okay, so they're sitting on top of that mesh or the bars. Okay? That's why you do it. But we're assuming compression bars, so we're going to find the development length for a compression bar. You have a tension bar, you have to do development length of a tension bar, and you may have to have a hook. Okay. All right, so we're going to do this, and then later, the next step will be to find this guy. Okay. But now I need to remember to change that F prime C, because I don't think I changed it. So, oh, see, I didn't change it here either, right? Yeah. So there is another place where I haven't changed it. Oh. So development length, this one, that was a tension one. Right. That's for your main bars. So we got 3 times 60,000 times 0.8 divided by 40 divided by 2.5 divided by the square root of 4,500. And that value is times 0.75. 16, so now it's even smaller, which is good. So 16.1. Yeah, all those decimals is because that came out from, as I said, from MathCAD, and they were doing all those decimals. Now you don't need all those decimals. 16.1, so it's greater, so yeah, we still can use the 17 inches, so that will not change. All right, so now I need to watch for that F prime C. Okay, so looking for this F prime C, we have then this development length in compression formula is there. That's what we used. So this value will change again. That will be now 4,500. And so we get 60,000 divided by 50 divided by the square root of 4,500. And that number is 17.9. So this one got bigger, 17.9. All right. Then the second equation doesn't depend on that. So 17.9. And so this one is 17.9 here, so that's going to be 18 now. Okay. So we got then 17.9, 17.9, and changes to 18 here. And available depth, they're the same. We got 22 is more than the 18, so we are good. Okay? And so notice here that is H, right? The cover, 3 inches. This is one of the bars, right? This is the other bar, so second layer. Okay. And this one is your dowel, the hook, okay? Because you need to, dowel doesn't count. So you have to stop before the hook that you got there. So that's what we're subtracting here. Okay? That's your number 7 bar. So number 6 bar, number 6 bar, number 7 bar. Okay? Because of the hook. Okay. So that satisfies that one. All right? So let's look at this available value. Go back to that figure there. Well, I can do it probably at the end. Do we have a sketch here? Yeah. So it will be H, right? Minus the cover, minus the horizontal bar, minus the other bar perpendicular to it, and minus the diameter of the hook, right? Because we're stopping right in here. Because remember, the hook doesn't count. So that's your LF. So right before that. So that's why you have that. So H minus 3 minus number 6, number 6, number 7. All right? All right. So we get that for that purpose. And that takes care of that anchorage part. Next, we need the splice on the top, right? Okay. We're having number 7 bars and number 8 bars. I did this on purpose because that way you can use that requirement in ACI 25551. You have different bars. Then you need to make sure that you find the development length of the smaller bar and you find your splice length, your development length here for the larger bar and your splice length for your smaller bar, right? And so we had to do all these formulas. So the number 7 gets all these formulas from the development length that we did. And this one is the development length of a compression bar, which is the number 8 bar, right? And we got all these formulas. Now you check all these numbers, right? And whatever is the largest, that's the one that controls. So in this case, 2625 controls. But remember, this is the development length of the larger bar and the splice length of the smaller bar. And you pick the largest of the numbers. Okay? And so 2625 controls, we say 28. So our splice length 28 inches, and that's what we put here as 28 inches. Okay? That's our split. And that's the end of this. As I said, I eliminated the rectangular and all that. I don't want you to look into that. But that will be another topic there. So this is what you need to complete your footings in your project. And that probably be the last thing you need to study for your exam. Any questions, you email me. We can always set up, collaborate. Next week looks pretty good. So pretty clear. So I'll be able to answer most questions pretty much at any time. All right. Okay, guys, good luck on your exams. I know you're going to have a busy week coming up. Anything I can do to help, just let me know. All right. Bye-bye.